Now, one thing which is rarely discussed in Swarm Robotics is goal seeking, and there's a reason for that because goal seeking and obstacle avoidance are two opposite behavior. Goal seeking will say, there is the goal, just go there, just go there. Obstacle avoidance will say there's obstacle, just stay away from there. So if you want to reach the goal, you have to go near to the obstacle. If you want to stay away from the obstacle, sometimes you'll just say, let's stay away from the goal. So the two behaviors are completely contradictory. The two behaviors are completely orthogonal. The two behaviors could be completely opposite. That goal seeking may involve getting close to the obstacle, and getting away from the obstacle may mean going away from the goal, and therefore a fusion is not the easiest thing to learn. But then of course you can always modify the equations to add goal seeking, and let's add goal seeking over here. So for goal seeking, I say it's plus another term which will be responsible for goal seeking. So let's say W4 times cos theta g, or I want to maximize it. So cos theta g is the angular deviation from goal. So I want the deviation from goal to be 0, and cosine of 0 will be 1. That's the maximum value. As the angular deviation increases, the cos theta g starts becoming from a value of 1 all the way up to 0. So it's cos theta g times W4. So let's say theta g is equal to angular deviation from goal so goal angle minus, okay, it's swarm robotics, so I don't know my current localization. So if you want to measure theta g in a swarm robots, of course what you do is that the goal emits a light. So the goal emits a light. So this is the goal, and that's a bright blue bulb. And this one has a omnidirectional sensor. So this light comes, falls around over here, and of course you look at the entire circumference and say, where is the light falling with respect to my location. So that gives you theta g, or the angular deviation from goal. We've used it in swarm robotics plus potential field to calculate the attractive potential. That's exactly how we calculated the attractive potential, by saying that I've got sensors which measure the relative direction to goal. So a light, the omnidirectional light sensor will sense, sound, array of microphones can sense, and so on and so forth. So we've already seen how to calculate theta g when doing swarm robotics with a potential field. So it's the same term around over here, and I just plug that up over here. It's taken cos because cos is invariant to in the first and the second quadrant. So the angular deviation is 30° plus or 30° minus. It's the same thing. So in terms of penalty, it's the same penalty, and that's why you see cost terms as 0. It could become negative. So sometimes it has to become negative. Let me give you an example. When this term necessarily has to be very bad, it has to be negative so that the robot does the correct thing. And let's take in a map like this. Let's take in some obstacles. Let's take in a goal. And let's take in a robot. So cos theta g is 0 because I'm facing the goal. I go here, I go here, I go here. But then as I go, this term becomes very bad away from obstacle. So now I don't care about the cos theta g. I don't care about the linear speed. I don't care about the angular speed. First, I need to take the opposite turn so that I don't hit the obstacle. Of course, then I'll again try. The angular deviation is increasing, but that doesn't matter. Then I'll again try, and that's how I'll go around over here. So in this region, you saw that the angular deviation cos theta g term was becoming from positive to negative. So that means the fitness will drop dramatically. But that's still okay for me because the penalty due to coming close to the obstacle is very bad. The moment you get a penalty due to obstacle, you had it. You absolutely had it. And that's something that you should be avoiding at any cost, anyhow. And therefore, reduction on the linear speed was okay. Increasing angular speed was okay, which is bad. It needs to be minimized. Even going away from the goal, making the cos theta term as 0, making this term of cos theta as negative was okay, but I did not want to take this penalty with me. And that's exactly what the robot did. It did not take that obstacle penalty. Um, there's another behavior that's sometimes discussed. It has a relevance in application, and that's called as a boundary following. I need to follow this boundary, so the robot should move like this. These are applications like patrolling, and I want my swarm of robots to do it, so they don't have high graded sensors for localization, they don't have the high graded encoders, they don't have nice rubber tires which don't slip. So all the problems. So let's take the robot at any general time, and then again I have sonar sensors. Now using the sonar sensor, it's easy to say that this one is facing the boundary, the one with the least value. So I do exactly the same thing. So fitness of X is I need to maximize my linear speed. So for entire time I have executed the physical robot, I need to maximize my linear speed. I need to minimize my angular speed. That's W2, that's omega 2. I need to be able to maintain a specific distance. So I want, let's say, this to be exactly 2 meter. So robot should always be at 2 meter from the obstacle boundary. It shouldn't go too close to the boundary. It should be exactly at 2 meters to the obstacle boundary. So now my nearest sonar sensor. So my nearest sonar sensor should return a value of 2 meter. If it's less than 2 meter, it's bad. It's about to collide. If it's large, it's bad. I mean, the robot had to take this route, and it's somewhere around over here, so it's not close to the boundary which I want it. So I want the value to be at an equilibrium, and therefore what I'll do is I'll give it a penalty based on the equilibrium. So I say di minus my threshold value 2 meter, or let's say in general term a b which I want to maintain, square divided by 2 sigma square and w3. So I want to reduce the penalty, so it's minus, and let's say this is d min, so I want it from this one, so I say d min is equal to minimum over I di t. So that's a very similar fitness function. All that it does is, this time, the moment the robot for any reason goes over here, this term will unnecessarily become large. The moment the robot comes here, this term will anyways become large. Of course, the angular speed will increase, so that's also bad. However, once it's at this point, what will happen is that if it doesn't reduce its linear speed, if it doesn't increase its angular speed, then this term becomes very small. So it becomes 1 meter, half a meter, 0.25 meter. It becomes extremely small. So it has to do something so as to avoid this penalty. This penalty can be extremely bad. So it needs to avoid this penalty, and in order to avoid this penalty, it will take a turn. This one is more important because many times in driving, what really happens is you see the vehicle in front and you're like, okay, I might collide, let's apply a brake, but still accident happens because there's a rate of deceleration, and at your speed, with the top retardation possible, with your impulses, you can still not slow down. So that's an equilibrium that sequential models they aim to get in. So you'll see in this scenario the robot slowing down well in advance so as to avoid a future buildup of penalty. Of course, it cannot suddenly make a 90-degree turn. So it will start reducing its speed, linear speed, and start increasing its angular speed well in time. Now, so far so good. So far, so good. There is a major problem over here. And that major problem over here is, let's say, what happened again. So, I had a robot, I got it from the market. I unshelled it up, it's a cheap robot, so I can purchase it in my own budget. I planted it in my lab. Then I said, hey, let's do neuroevolution, let's do evolutionary robotics, it's hot. I don't need to program it up. I'll just switch it on. Today it's a long weekend, so Friday morning I install it up, and by Monday morning it'll be there. It'll be working very good. So with this aim, you start the program. Now there are five. Let's say there are 10 individuals in the population. So let's draw the lab and see what's the issue. So this is the lab where I work. There are some obstacles. And this is a new addition to the family. That's a robot. So there are 10 neural networks. I load the first one for let's say 3 seconds, and it goes over here. It'll get a good fitness function value because linear speed is maximum, angular speed is minimum, and the distance from obstacle was anyways large. Now the problem is the second, so that's the fitness evaluation of the first individual. Now what happens is I load the second individual to calculate its fitness function value. Now look at it, it's already at a very bad shape. So it just moves 2 steps more and it gets a very high penalty value. It's not its fault. The first network made it very bad. Now it's trying to take a turn while still coming close. Now it's not its fault. It's the fault because it's a bad starting criterion. So this is fitness evaluation of the second individual. So the poor fitness function value is just because of a bad starting point, and so on and so forth, third, fourth, fifth, and so on. Of course, it would have been fair if I would have took the robot, kept it at exactly the same starting place so that all individuals, they start from exactly the same location. However, I don't want any human interference. I don't want to say that I'll depute a human who will do only this thing. After the first fitness function calculation for the first recurrent neural network, somebody takes the robot and puts it in the starting location. Then after the second takes it, puts it at the starting location. Third puts it at the starting location. If I can invest so much in manpower, I'll just employ a manpower to program the robot. Problems of human bias, of course, still there, but maybe the human can program it better than neuroevolution. So now what I need to do is that's a problem. It's not a very big problem, but it's still a problem that sometimes an individual will start from a bad location and therefore get a bad fitness function value. The other problem is that this network takes in a very, 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 very long time. So imagine at the least how many? 100 individuals? And at least how many? 250 generations? How many fitness function evaluations? 250 into 100? The least. Too many parameters, it will require more than that. Now you run every individual for 4 or 5 seconds. So the entire population for this very modest calculation will also be, the time required becomes 100 individuals into 250 generations into 5 seconds per fitness evaluation. And that's not even close to realistic, and that's too much time. So now you make use of a fact that what really happens in any evolutionary technique, including neuroevolution, the initial population is always random. Some of them are good, but then they are too good. Some of them are bad, they are too bad. Most of them are too bad. You just get a few individuals who are reasonable. Most of them are at random places. There are only few which are reasonably close to a local or global optima. And therefore, what you say is that the first problem, some individuals start from great place, some individuals start from worst place. That is not going to be a problem, because even if the individuals whose fitness got unluckily down only because it started from a bad place, and an individual survives only because it starts from an interesting place, the next time luck will not play in the favor of the second individual who survived. Second generation, it will die off. While an individual which is good no matter what place, which is the individual that we want to find, it will survive no matter where you start from. So the first problem is not really that hard. So what I say is that finally I need to get individuals who are good irrespective of how the individuals start off. So luck can play a role one time, but a bad individual is bound to be eventually deleted, and a good individual which performs best in any starting point, it's bound to survive. So the initial few iterations could be randomness, because of the randomness in the fitness evaluation, because every individual starts from a new place, some from more easy places, some from the more difficult places, but the effect is not that long. The second one is also that I'm running everyone for 5 seconds. Now, I mean, 5 seconds, can you really see how a person is behaving and judge the person? Does any company recruit like this? No. So 5 seconds is already on a pretty extremely small level, and because it's already on an extremely small level, I cannot reduce that up. However, there is one thing that we do, and there is one thing that we say, that in general this is delta t. So delta t is very small initially, and delta t is very large at the later generations. Now, what happens initially? So initially what happens that most of the individuals are bad. Most of the individuals are bad, and because most of the individuals are bad, you don't require much time to judge a person. I mean, if we take in random students from the entire country and we just want to find out how good or bad it is, you can give one question, two question. Harder ones, the good ones will be able to do both of them. Most of them will not be able to do both of them. So two questions are enough. Later on, when we come to a cohort that these are the individuals after some entrance test and blah blah, after all kind of scrutiny, then you got competitive individual. Then I cannot do this. If I give just two questions, either all of you will do both of them or none of you will do both of them. It's not discriminating. Then I need to give you lots of questions so as to really make a mark sheet, so as to really make a roll call, so as to really make in a sorted sequence as per your performance, so that I can give you grades. So that's why we do a lot of exercises, lots of questions, and so on and so forth, so that I can have a recent, decent, fair enough idea. And that's exactly the thing. So initially, the neural networks are random. One or two of thousands are very good. Rest of them are bad. So I'd say just few seconds, a few milliseconds are also good. However, later when all the individuals are competitive, most of them have converged. There are 3-4 local optimas where they lie. I really need to decide which one is the most competitive, which one is the best one. Then I do all the thing that, okay, let us run them for a prolonged time so as to see their performance measure. And that helps me in order to control the evaluation, and that helps me in order to control in the execution time to a reasonable extent.